So in this video, I wanted to help some of you finish out pages 13 and 14, the stoichiometry problems that I didn't do in podcast 9.3. And I also wanted to present you with kind of an alternate way of solving these problems. And I think most students in most classes managed to kind of follow along and work out a few problems with me like this in class, but I also know that some of you were watching that original podcast during class because you hadn't done that already, and so I wanted to put this all in a video so that you could access this, and this might help you, it might not. In the original podcast, if you remember, I used this map in order to help kind of navigate each problem and figure out how to solve it, but like I pointed out in class, the problem with a map that you don't really understand, and this is a lot more complicated than the other map that I had used in the past to help people, is that if you don't know where you're starting or where you're trying to end, or if you can't find that or really know for certain and be confident in that point, then how are you ever going to navigate in between those points? You're just going to be lost the whole time anyway. So if this is too complicated or weird and you just don't know how to navigate with it, then I'm going to instead use this table that I showed you in class. It's basically just a list of all of the possible stoichiometry conversions that we can do, and kind of show you how you can use this like a checklist in each problem in order to figure out what you need to do and set up the stoichiometry problem. Now, I'm altering this a little bit from what I showed you in class. I'm pulling that volume ratio out of kind of the rest of the table, because this is kind of a special situation where if you've got any problem that starts with liters and ends with liters, two different substances, it says like how many liters of carbon dioxide will be formed if I burn this many liters of methane gas. Liters to liters, you can just use the balanced coefficients from the balanced chemical equations in order to convert from one substance to another in liters, and that's all you're going to need to do. So any problem, it's liters to liters, use that shortcut. That's kind of its own standalone kind of conversion, and that should always be the first thing you're looking for, because that's going to be the easiest way to solve those problems. Now, if it's not liters to liters, it means we're going to have to go down to the rest of these conversions. And you'll see that the first conversion in the rest of this table is the mole ratio, which is basically the same thing as that liter ratio we were just talking about. In fact, this is our go-to. This is what all stoichiometry usually comes back to, is this ratio of moles coming from that balanced chemical equation. So every problem is going to rely on you having a balanced chemical equation and using that to convert from one substance to another by this mole ratio. So really, this is a standalone kind of conversion list for when you're doing the stoichiometry, but step one in every single stoichiometry problem is going to be to either write and or balance a chemical equation, because that's going to be kind of what we're using as our replacement map here, because that is what everything in the problem is going to come back to. So if you've got one already written for you, just balance it. We're going to need it balanced one way or the other for this mole ratio. If it isn't written for you, you need to put some effort into making sure it's written correctly and then balanced correctly, because that's going to make or break your problem. Now, everything else in this table comes back to the mole. If you see down here, everything else is set equal to 1 mole. So the units in your given and your unknown might be a mole, they might not. It might say how many moles of carbon dioxide are needed. That would make your problem easier, because then you won't have to come down here and turn those moles into something else. But if you do, we can always get back to that mole ratio. So if your given or your unknown has grams, mass there, then we're going to have to add up that mass of that substance from the periodic table, find its molar mass, and use that in order to get to moles and do that mole ratio. We need molecules, or if we've got molecules, then we've got Avogadro's number to help us. If we got liters, then the easiest way to get from liters to moles is to use that 22.4 number. But if you remember, we can only use that when we're at our standard temperature and pressure, STP, which is 1 atmosphere and 273 Kelvin. And there are some other variations, different units of that. But if we're not at those conditions, we cannot use 22.4. But even below this, I've put a little cheat sheet to remind you if we are not at STP and we need to be going from liters to moles, then I have rearranged this ideal gas law to help us solve for our moles or our volume if we're at some kind of different temperature and pressure. So I would just need to know that new temperature and pressure, choose the correct R, and the problem would have to tell you that volume or those moles to be able to find the other one. But we can do it the equation way if we need to, and then do the rest of the stoichiometry once we've got the volume or the moles that we needed. So this is really kind of a checklist for you. When you look at a problem, first look for liters to liters. If so, just do that ratio one step and you're done. If not, we're going to have to come down and look at the rest of this. So that's what we're going to be doing as we work out a couple problems on page 13 and 14. So let's go ahead and look at that packet. This is page 13. Number 2 is the very first question that I hadn't done in our podcast. And when we balance that equation, 1, 2, 2, 1, it's always our first step when looking at a new problem. Now I'm going to look for my given and my unknown. And so my number, what I've got is 15.5 liters of methane. So methane is CH4, and it's telling me that I have 15.5 liters of this stuff going into my reaction, and it wants us to calculate the volume of carbon dioxide produced. So carbon dioxide is what I'm looking for, and it wants volume, which means liters of carbon dioxide. So once we have this problem kind of diagrammed here with our chemical reaction, we know we're going to need this 1-to-1 ratio eventually. It's going to happen no matter what. And when we look back at our checklist, turn this off to get that to pop up. Looking back at this checklist, the first thing that we need to be looking for are volume ratio. Are we going from liters to liters? Well, yes, we are. So evidently, all we're going to have to do is use the coefficients from that balanced equation, that 1-to-1 ratio. I'll plug those in here. And we're going to say 1 liter of A, and A is the substance we're starting with, that's CH4, that methane, and is going to be equal to 1 liter of B, that carbon dioxide that we're looking for. So this is going to be the only ratio that we're going to need in order to be able to set up and solve that last question. So let's head back to the packet. And to start all stoichiometry problems, the first number we always write on our line, remember, is our given, the number that we had from the problem, 15.5 liters of methane. Number, unit, substance. Then we can put our next vertical line, vertical divider, between the next step. And if you remember, we always go down to the bottom, and that bottom part has to be the exact same substance and unit as the previous number that was up on top of the last bracket. And here, that means we're going to be putting this 1 liter of CH4 on bottom, and our whole goal was to use this mole ratio to convert to that CO2. So we're putting the 1 liter CO2 on top. My line didn't have to be this long after all. And now we're done with this setup. All we've got to do in order to actually solve this problem is multiply those numbers on top. 15.5 times 1 and then divide by any numbers on the bottom, divided by 1. In this situation, that number is not going to be changing very much. It's going to come out to be 15.5, but the important part is that the top units and the bottom units cancel out. Liters CH4 are gone, so now this is what we are looking for, liters of CO2. And that is our answer. So this was that nice short liters to liters, just as simple as our moles to moles problems. Now, let's look at one that's not quite this simple. Down at the bottom of this page, question number 4 is, first we're going to need to write a balanced equation. So if we read through here, it says that chlorine gas is going to be making some hydrogen chloride gas. So I imagine that in addition to the chlorine that they're giving us, and they're telling us about, in order to be able to make that hydrogen chloride, I'm probably going to need to be adding some hydrogen gas to that as well. So that is the basics of my reaction, and now I need to balance it. 2 there gets it balanced. I am going to write my 1s in just to help me visualize my ratio a little bit better. And now let's reread the problem and put those kind of notations on this reaction. Make a note of what our substances are that we care about in this reaction and what units are on those substances. So it says to calculate the volume of chlorine gas. So I want to know about chlorine gas, and because it wants volume, that means liters. So I'm going to have to be getting liters of chlorine gas as my answer, and evidently I want to figure out how much chlorine gas I need to make 75.3 grams of hydrogen chloride. So that's the number I'm going to be putting into my calculation here. Even though that's the substance I want to be getting out of my reaction, we're just trying to work backwards and figure out how much stuff we need to get what we want from this reaction. So, looking at this, we can already see this 1-to-2 ratio is going to be important to us because that's our chlorine to hydrogen chloride ratio. And if we look at our units, we are starting, I do see liters there, but because we're not going directly from liters to liters, going back to our little checklist here, we are not really going to want to use this volume ratio. We could, but that's one of the confusing things about the map, is that you can actually take yourself around in circles and circles and circles, and that's not going to help anyone. So, if we're not going from liters to liters, we're going to treat those coefficients from the balanced equation like moles. And that's just going to make everyone's life easier. Just convert our substances using a mole ratio, because everything else can be converted to moles or out of moles very, very easily in one step. So, because we have grams as our given, we're going to need to find the molar mass of that HCl stuff, just adding up H and Cl from the periodic table, which FYI, H is 1.008 and Cl is 35.453. So if we add that up, HCl is 36.461 grams per mole. Just trying to make that a little bit more transparent. I know normally I'll just give you that number if I'm working out a problem and kind of tell you what I'm adding up, but I want you to make sure you're confident in how you can add up that number. Just find them on the periodic table, put them together. So we're going to be using that conversion shortly. And then it also had liters. And so we're wanting to use this 22.4 liter conversion as well, as long as we are at STP. And if you read through that problem, I don't have it up on my screen right now, but if you look at the problem, it does say right there at the end that we're at STP. So I can use this conversion to help me get there. Otherwise, I would have to be doing something like this. But that's not the case here. Let's get back to our packet. All right, so here we are in our packet. That's the at STP part of the problem that does tell us that we're going to be able to use the idea that 1 mole is equal to 22.4 liters. And over here is where we said with our grams, we were going to need our molar mass. This many grams equals a mole. And so now our problem's all set up. All of this stuff that I've put down here is all numbers we're going to have to use. This is kind of, like I've said before, kind of a sneaky, not so traditional guess method that you might have heard or seen before, the given unknown equation substitute solve. That's what we just did here, is that we just kind of labeled our given and our unknown on our chemical equation and then use that to choose what equations we're going to need to use. And now we're ready to set up and solve our stoichiometry problem. So let's go ahead and do it. Our given is always our starting number, 73.5. Oop, I just got that backwards. 75.3 grams of our HCl. And then if I'm right here, my bridge to get to my next step is that 36.461 grams equals 1 mole. Because I've got grams of HCl up here on top, I'm going to put the grams part of that equation on bottom, making sure that that substance gets there. We're still on that HCl side of things. Opposite side is going to be the 1 mole. That equation stays together. It's just deciding which one goes on top or on bottom of this bracket. So now we're at moles. We can use this as our mole ratio if it helps you. Maybe after we decide that we're using this as a mole ratio, you could even write in the word mole there so you can see that this is 2 moles of HCl to 1 mole of chlorine. We're going to put the HCl stuff on bottom because I had HCl on top before. So 2 mole HCl on bottom, 1 mole Cl2 on top. And I'm going to have to make my line longer because we're not quite done. We want to know liters, and we are only at moles right now. And so we can see our path to get there involves using this 1 mole equals 22.4 liters. And because I have moles on top here, I'm going to put the 1 mole part of that equation on the bottom, making sure that now I'm working with chlorine on the chlorine side of that reaction. So that's the substance I'm using. And now that's the answer that we were looking for. Volume of chlorine gas, liters chlorine, Cl2. So in order to finish this problem out, we should multiply all the numbers that are on top, divide by all the numbers that are on bottom in order to get our final answer, which you could even check in those posted answers if you remember. But 23.1 liters Cl2 is going to be our final full correct answer there. If you're not getting that answer, please let me know, because if you're looking at this setup and you get it all perfectly set up, but you're uncertain of how to put it in the calculator and get that final answer, that's something that I can help you with in 5-10 minutes, and we can get that figured out, fixed up in a way that makes sense to both you and me, and getting you the points that you deserve for all the work that you've done. So please let me know if you're still struggling with that part of things. But let's go ahead and look at another problem. Page 14. I worked a couple problems in the podcast, and then I left a couple, and I'd like to finish out that page 14 with you. So let's go ahead and start on question number 3. If I scroll down here, we've already got an equation written. It's not balanced though. There might be some balanced equations on your test, but probably not too many. So we need to work on some balancing skills maybe one last time before we get to that point. And now reading through, it says, what mass of potassium chlorate, so here's my potassium chlorate, and it wants mass, so that means grams is what I am looking for, would be needed to produce 11.2 liters of oxygen. Okay, so that's what I've got. And the number I'm going to be putting into all the rest of this is 11.2 liters. And I want to get grams of KClO3 out. And then it continues to tell me at 50 kPa and 37 degrees Celsius. So we've got our problem, and I know I'm going to need to use this 2-to-3 ratio eventually. And because this is not a liters to liters problem like the first one we put together, I'm probably going to need more numbers, more conversions to help than just that 2-to-3 ratio. So I do have liters, but I'm going to want to get to grams this time. So this is kind of sort of the opposite of that last problem we worked out, because we're starting with the liters and trying to get to grams. But if we look back at our conversion checklist here, we already know we're not going to use this volume ratio shortcut. So I could go ahead and label those coefficients moles when we get back there. I'm definitely going to need to find the molar mass of that KClO3 stuff if I'm going to want to be able to find the grams for it. But when I'm looking at my liters conversion that I'm thinking I might need to use with those liters that I was given, I notice that it reminds me I can only do that when we're at STP. And that problem is not at STP. Firstly, it didn't say it. It didn't see those 3 letters anywhere. And if you go back and check page 3 in your packet, STP is 101.3 kPa, which is not the same that we're at. We're at 50 kPa. And STP is 0 Celsius, and we're at 37 Celsius. So because we are not at STP, we cannot use this shortcut. But there is hope. 2 blue asterisks. If we need to convert from liters to moles, we can use our ideal gas law in order to do that, using one of these equations. So we're going to go back and look at that situation. Really, I'm going to start from this equation, that PV equals nRT, because I'm not looking at my problem at the moment. And so I don't remember, am I looking for moles or volume? But that's going to be a lot clearer when we're looking at the problem. So I need that molar mass of our KClO3, which is 122.548 if we add up 1 K, 1 Cl, and 3 oxygens from KClO3. So I'm going to use this number, and then PV equals nRT. So that's kind of my checklist. It's like, okay, I'm ready for this, and then one of these 2. So back at the packet, I'm going to write down that 122.548 grams equals 1 mole. I'm going to go ahead and label these as moles here. And that helps me see this problem that I've already kind of written out for myself. I'm trying to get from liters to moles using that ideal gas law. That was my plan. And so that means I'm going to be trying to solve for moles. I'm going to solve for N here. So I'm going to go ahead and write out that equation, rewritten, solving for N, which is going to be opposite PV over neighbors RT. And this should be everything that I need to solve this problem. And this first step using the number that I'm given is actually not any kind of stoichiometry. That's this equation that I was just setting up here. So let's go ahead and finish setting this up and working this out. The P pressure that we're at non-standard 50 kPa, the volume it gave us was 11.2. And then we have R, because we're in kPa. If you go back and look at page 9 where we introduced this ideal gas law, that's where all the R's are written. Page 9, the R that goes with kPa is 8.31. And then the temperature we're at is 37 Celsius, which if we add 273 to turn that into Kelvin, it's going to be 310 Kelvin. So now we've got all of that together. We can multiply those numbers on top, divide by numbers on bottom, almost as if it was a stoichiometry problem. Just plugging that in. That would be my recommendation. Let's do this times this, divided by, and divided by, to make sure that that turns out correctly. And our answer for our number of moles is 0.217 moles. But that's not our answer. That's just this first step, taking our volume and turning it into moles, so that now we can start the actual stoichiometry process of going from these moles of oxygen, which would be an important part to note as we're writing this number down, getting started for some stoichiometry. Need that substance on it, and that's still on this oxygen side of things, at least until we use this 2-to-3 ratio, making sure, because oxygen is on top, we put the oxygen part on bottom, which means 2 moles of KClO3 on top. So now we've gotten to moles of KClO3, and the last step to getting to our grams is going to be this molar mass that we added up. So the moles part of that, 1 mole specifically, is going to go on bottom, and then the 122 number goes on top, so that we end up with grams. And that's the end of our stoichiometry, which means we can stop and multiply and divide again. It's kind of a pain to do this in 2 separate pieces, but we don't really have a choice. When we're not at STP, we have to do this calculation separately. But putting all of these numbers together now, we should get 17.7 grams of KClO3. Once again, if you're having trouble with how to translate this into calculator stuff, let me know, or talk to one of your classmates. Someone will be able to help you with that part pretty quick and easy. Now let's finish out page 14 with this next reaction. This last problem. It looks like it's a little bit lengthier. There's a lot more writing here. So let's make sure we don't miss any of those details. It says, when sodium reacts with water, how many grams of sodium? So we're looking for grams of sodium. And I didn't balance this. Give me a moment. Okay, so we care about this sodium, and we're going to want to know some number of grams by the end of this. Are required to produce 6.5 liters of hydrogen gas. Okay, so the hydrogen is what we're creating, and that's going to be 6.5 liters as our starting point number to put into there. And then it proceeds to say, over water at 30 degrees Celsius and a total pressure of 671 millimeters mercury. Partial pressure of water vapor is 31.8 millimeters mercury. Okay, that is a lot of other stuff going on there. But what I'm noticing is, first, I'm not liters to liters. I'm going to go back to my checklist. So, in this situation, We were already observing we're not going from liters to liters. That's a special situation, and you're not going to see a whole lot of them. But, it could happen. So we're going to treat those coefficients like moles, use them as a mole ratio to convert from one substance to another. And it did want us to find grams of sodium. So luckily that is just sodium, not any crazy compound. So we can just look at Na on the periodic table, and that's going to be the molar mass we're going to be using there. And then we're starting with liters. So I'd like to be able to use this 22.4, but we are not at STP. So once again, we're going to have to be turning our liters into moles using our PV equals nRT ideal gas law, rearranging that to solve for moles, and then using those moles in some stoichiometry, a lot like the last problem, just a new reaction to do it with. So let's get back to that packet. Okay, so back at our packet, I've added in our molar mass for the sodium over there, as well as our same equation we just saw in question 3 to find our moles. But there's a lot more detail in that problem. As we're reading through to maybe plug some of our numbers into this equation, notice that it gives us a temperature, which adding 273 to turn that into Kelvin is going to make that 303 Kelvin. So that's going to be our temperature. But then it says a total pressure of 671 millimeters of mercury, and tells us the partial pressure of water is 31.8 millimeters of mercury, down underneath this little red scribble of mine. So that's telling me that this pressure that we see over here that I just underlined is not actually the pressure that we're going to want to plug in for our P. That's the total pressure. Evidently, because this was collected over water, there's some water pressure in there. So we need to subtract that out real quick. So subtract 31.8 is going to give us 640. Nice round number. And we are going to keep one decimal place because both of those numbers had one decimal place in them. And so that is our pressure that we're going to be plugging in to here. So let's go ahead and use that. 640. Our volume that we're working with is that 6.5 liters. There's a 0 up in the problem that I had failed to note here. And now we've got R to deal with. And since this is mmHg, means we're going to be using that 62.4 number. Go back and look at page 9 if you need to see why. The 62.4 is the number that has mmHg in its units. And then we have that 303 Kelvin for our temperature. And with all of that all together, we end up with an N equal to 0.220, 3 sig figs there, moles. And that is technically on the hydrogen side of things. This isn't our final answer. We don't really need to put a big old label on that, but that might make it clearer as I'm getting started here with the rest of my journey, because that's only our first step, getting our moles of hydrogen so that we can be trying to get to grams of sodium from it using our stoichiometry. And so with moles of hydrogen being where I'm at, I'm going to use this 1 to 2 ratio here, making sure hydrogen is on the bottom, which means sodium is on top. And now that I've got moles of sodium, I'm going to get to the grams using this molar mass. So 1 mole Na, 22.99 grams. And that's it. Setting this up, calculating my answer by multiplying all of the numbers on top together, dividing by well, I guess we don't really have to divide by 1. It won't change any of the numbers, but sometimes it's that process that helps make us more confident in our answer. And this should end up giving me a final answer of 10.1 grams of sodium. So that's the end of page 14. Page 15 and 16 are where I'd like you to start trying these out on your own. The next problem has more grams and liters. Remember, with each of these questions, there's going to be a lot of liters in there because that's an easy way to measure gases. Just make sure to check. If you're at STP, take the shortcut. But if you're not at STP, it's really not that bad to do a quick little ideal gas law calculation off to the side before we start our stoichiometry with the answer from that calculation. Just have to be cognizant of that and do it when you need it. So let me know if you have any other questions. I hope this helped.